Welcome back to another episode of Dave Does Math from Home. We have an exciting one for you today. Today we are talking about section 16.2. This is going to be a pretty direct continuation of the stuff we did in 16.1. In 16.1 we broached the topic of double integrals, especially in terms of double integrals over rectangular regions. Which is a good way to get into double integrals. We're going to extend that today. We're still talking about double integrals, where we have some region on the xy axis and some function, some surface doing whatever it is doing above that region on the xy plane. And we want to integrate that function over that region to find the total volume of space beneath the surface, that function surface, over that region. The big difference today is, in the last section, the regions were all rectangles. They were very square. They had nice right angles, all rectangles all the time. Because all of our regions on the xy plane were defined by, we had whatever f of xy was going on here. They were defined by dx, dy, and x and y were always constants. If we wanted to go from 1 to 3 here and so we got y is 5 to 9 here, it doesn't matter what the function is. This is sort of not important. These bounds will always define a rectangle. If x is going from 1 to 3, that gives you straight lines. And if y is going from 5 to 9, you've got more straight lines. If you have all of these perpendicular straight lines, that's what gives you the rectangle. It comes from these bounds. Anytime you do a double integral and you have constants for these x and y value bounds, you will always get a rectangle. All the time, every time. These constant functions are straight lines, gives you a rectangle. So today's topic is, I want to be able to do these double integrals to find the volume under surfaces over regions. I want to extend that beyond rectangles. Rectangles are nice. Rectangles are a great tool for learning. Rectangles are boring. I want to do triangles. I want to do circles. I want to do parabolas. I want to do weird, goofy wave functions. I want to be able to define any region on the xy plane using functions, and I want to be able to do a double integral over that region, no matter how weird or goofy or bizarre or wiggly its shape is. And that is what we're doing today. So we're going to extend this idea of double integrals into shapes. And hopefully you are guessing by my emphasis on these bounds being constants turning into rectangles, hopefully you are realizing that we can get goofy shapes by messing with these bounds. Messing with these bounds is exactly what the plan is, but it's probably not going to be as intuitive as you're hoping. It will become intuitive with a little practice, but it's not going to start out that way. So bear with me, pay close attention. We will try to do this as painlessly as possible. To start off with, I want to talk about this region 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6. So I want to define a region here with the function y equals 1. I'm not going to call this a constant anymore. It is a constant function, but for now, the salient part is that this is a function. This is the y equals 1 function. And here we'll find the x equals 2 function. Here's the point 2, 5. Here's the point 2, 1. Here's the point 1, 9. And here is a line. This is the line y equals negative 1/2 x plus 6. It goes from 2, 5 to 1, 9. And together with this stuff, it makes a very nice triangle. I want to integrate a function over this triangle. And again, it doesn't matter what the function is. The function will determine the height and whatever surface is going on above this triangle, but the region itself is not directly related to that. So there's going to be two big parts to these problems. The first part is going to be figuring out what region you're working with and setting up the integral with the correct bounds so that it represents that region. That's the first big part. You set up the integral with the right bounds to give you this region of space. The second part is going to be when we actually evaluate that double integral, which is going to be super exciting. That part, honestly, is not changing much from what we did in the last section. So that second part, that's where the actual function you're integrating matters, the surface above this area. That will matter when you actually start evaluating the integral and getting your volume here. But it doesn't have anything to do with defining the region or the boundaries or setting up your integral. So I'll eventually, the function that I want to integrate will be x times y. And we'll talk about how to integrate that later. But for now, first, I just want to talk about how to set up the integral. So a lot of this is going to have some commonality with what we did in Calc 2 when we were doing areas between curves and volumes of rotation. When we were doing those sections, that was section 6.2, 6.3, and 6.4 from this same textbook, if you're curious. When we were doing those sections, our first order of business was to draw a picture, like this, which we've already done. The second order of business was we were choosing whether we were going to slice this thing vertically or horizontally, which mattered a lot with when we were doing volumes of rotation. The direction of slices sort of either gave you washers or donuts or discs or whatever, or I think the book calls them shells. I call them pipes. Little hollow, round cylinders like this. So the direction you sliced it mattered a lot. It changed what you were doing. And the same thing is true here. We have to make a choice. Eventually, we are going to slice it both ways because we want to get all these little slices of dx and dy. And when we cut it up both ways, we'll get those little squares of area, the dx, dy area squares that we're going to find the volume of the pillars over. We talked about that in section 16.1. So eventually it's going to get sliced both ways, but we need to figure out which way we're slicing first, because that's going to change how we do this. So I like to slice vertically first. Sometimes that's a really bad plan, but all things being equal, and in this triangle all things are pretty much equal, vertical slices first I think is easiest. So when we slice this thing vertically, we have to look at the bounds we have here. Ultimately, we are going to be setting up a double integral of this function x times y. If I slice y first, that means I'm doing dy dx. for my d's. It's very literally y first. And when you slice it this way, you have to look at what is the lower bound on y. The lower bound on y is 1. It's this function right here. Lower bound. The upper bound on y is this function. So y equals negative 1/2 x plus 6. The function is the upper bound in the exact same way that this function is the lower bound. I mentioned a couple minutes ago that I was going to stop calling these constants and start referring to them as functions, and this is why. The big paradigm shift that we have to get used to in this section is we are now using functions as bounds in integrals. It's not just numbers anymore. So, if your dy is here, that means that right here, you've got yourself a y as a function of x. And this is also y as a function. It's not a function of x because it's a constant function. But it could be if we wanted it to be. So these are the bounds on y. Here's where things are going to get a little tricky. Once you've finished this integral on y, you integrate this function with respect to y, and then you get your what, y squared over 2. Actually, let me make this 2xy so I don't have to deal with fractions as much. Actually, there's a fraction right there. Let's make it yeah, let's make it 8xy. No fractions allowed. Okay, changing things up a little bit. I have my 8xy here. I'm going to integrate that. Once you integrate it and you get your y squared and you're plugging in your y equals 1 and you plug in your y equals negative 1/2 x plus 6, and then you simplify all the business that's going on in there and you have just x's, then you get to start the second integral, the outside integral, with your dx's. And there was something I said in the last section, in section 16.1, something I said about how the integral sort of progresses as throughout the problem, and that is, once you integrate with respect to y, there's no more y's. All of the y's are gone. Which is going to happen. When we integrate with respect to y, we're going to replace y with 1 on the bottom, and we're going to replace y with a function of x on the top. And after that, you will have nothing but x's, which is what we want. At that point, you can't put y's back in. Once you've finished that process, y is done. Y is finished. Y is no longer a part of this problem. Integrating on y first is like collapsing this dimension. You've already got all of this area, it's done. It collapses and now it's basically a straight line. And the point I'm trying to get to with all of this is the outside integral is never a function with variables. The outside integral is always constants. Once you've sort of collapsed this triangle bit and you're just working with the distance from x equals here to here, you're not going to use this function again. You're just going to put in x is 2 and x is 9. So this is the part that's kind of tricky for a lot of students to get into the theme of. The bounds on the inside integral are going to be a function, are going to be functions of the outside variable, so that when you do that integral, the y's disappear and all you have left are x's. The bounds on the outside integral are just numbers, always just numbers. Throughout all of the different integrals we're going to be doing, outside bounds, always just numbers, never functions. If these outside bounds are functions, then you are, like, once you evaluate on these function things with variables in, you're going to get a volume with variables in. And that's not what we want to do, like, ever. Outside bounds are always numbers, so that you plug them into the function. Your answers to all of these problems should be just numbers by the time you're finished with all the integrals. So, We can work on this integral. Before I actually start doing the integration, or yeah, let me just do the integration here, and then, because the other thing I want to talk about, and I might have to do that in a second video because we're already at 15 minutes. This is heavy stuff. I apologize. The other thing I want to talk about is what this integral looks like if you do it the other way. So it shouldn't super matter whether you do it with x first or y first. You should be able to swap those things and do x first. And the function will stay the same, 8xy, that's not going to change, but your bounds will be different. Okay, I will talk about this now, and then in the second video I will evaluate both of these integrals and we can see what happens. So, if you switch the order, so now we're slicing this thing horizontally first, and again, we're slicing it both ways eventually. It's just what you're slicing first. Then your bounds on the x-axis need to go from x equals 2. That's your lower bound. It's always this constant function, x equals 2. And they need to go to this function, but they need to go to this function after it has been solved for x. So this bound needs to be an x equals something. You can't use y equals 1/2 x plus 6 as a bound on x. It has to be x equals. Which is why I really like writing these x equals things. The book is not going to do this. The book is just going to put a number here and a function here, or function and number. I don't like that. I like having the entire equation as the bound, because that helps me correlate these x's, y's. Anyway, we need to solve this thing for x so that this function solved for x can be the upper bound here. So I'm going to subtract 6 from both sides and get y minus 6 equals negative 1/2 x. And then I'm going to multiply both sides by negative 2. So I get negative 2y plus 12 equals x. So, does that really have an x-intercept of 12? Does it not have an intercept of 9 over here? Did I make some kind of mistake? Oh yeah, sorry, this isn't 1, 9. This is, when you plug in 1 here, this is, no, when you plug in 1 for y, you get negative 5 divided by negative 1/2. This should be 10. Sorry. 1/10 is that point. Whoops. Okay, yeah, now I'm convinced that this intercept is 12, because if you go one more unit down, it's 2 more units to the right, and that gets you to 12. Good, we solved the mystery. So, this should be negative 2y plus 12. That's your upper bound on x. If we're doing x as the inside bounds, where we get to use functions of y, that means that y, as the outside bounds, have to just be constants. It's like we're collapsing this dimension, and the only thing you have left is this line on the y-axis that goes from 1 to 5. So y is 1, and y is 5. And this is the setup for the integral if you want to do x first. And both of them are perfectly valid. They should get you the exact same answer. I will demonstrate that, assuming I don't make any more bizarre arithmetic mistakes. I will demonstrate that in the next video, which will start right after this